So first things first, I want to apologize for not being there, making it back on Monday. I don't want to get too far behind, so I wanted to at least introduce some of the topics that we'll be dealing with this week, which is partial differential equations, so brief introduction to those. And then we're going to derive the first equation that we're going to solve, and then deal with the actual solution, all the details, all the hard stuff on Wednesday. So hopefully this isn't going to be that bad for what we need to do today for Monday. So let's get to it. So first bit of business, this wouldn't be a Monday class without homework. So week 8 homework due next Wednesday, March 27th as usual. Only 3 questions, and this is not like my usual 3 questions where it takes a long time. These are easy 3 questions, so getting you back to spring break, kind of a nice easy transition. Another reason why I wanted to not get too far behind is because on April 1st we actually don't have class, and this is not an April Fool's joke. It's real. We do not have class. It's because of the building that we're in. Farley, the journalism school, has an annual high school event where they take over the entire classroom or the entire building, and so our classroom gets canceled, unfortunately. Usually they tell me before the semester. This year they did it late, that's why it's not on the schedule, but that is another day that we are not going to have class. Haven't decided yet to kind of see where we are, whether I have to do another one of these videos or not, but at this point that's where we are. So that's administrative stuff. Now we'll get to the actual partial differential equations part. So partial differential equations, also known as PDEs, different than ordinary differential equations. Ordinary differential equations only depend on one variable, so y only depends on x. Here we have more than one variable that it depends on, so I have a multivariable function depending on more than one thing, usually space and time. So usually there's a t variable, so there's a derivative with respect to t, and there's a spatial variable x, y, or z, and or could be even more of those. So I have some x derivatives, some y derivatives, maybe some z derivatives, depending on how complicated it is. First two we're going to see are just called one-dimensional, referring to the spatial dimension. So one spatial dimension x, one time derivative t, and that's the equation that we usually see. Ones we're going to see near the end of the course involve x and y. It's a bit more complicated there. So basic concepts in terms of notation. Basically the exact same stuff we learned for ordinary differential equations works for partial differential equations as well. Linearity, whatever the dependent variable is, can't be multiplied by itself. Homogeneous, the right hand side 0, all that's exactly the same. Even the order means the same thing. The only kind of tricky thing about this is that you have two different variables you're differentiating with respect to. You could have x derivatives and t derivatives. Again, it's the highest one, and it's the highest of either one. So if I have 3 t derivatives, 2 x derivatives, order is 3. So we'll see an example of that later after I derive the equation today. The other thing is that there's no sense using primes for derivatives anymore, because prime, y prime, what does that mean? Is that with respect to t, with respect to x? So instead of using primes, we now use subscripts as a shorthand notation. So that instead of having to write the full partial u, partial x, I can just write u subscript x as a shortcut. Same thing for second derivative of u with respect to t. I have utt for that. So the equation to be derived is the one-dimensional wave equation. Here one-dimensional means one spatial dimension, so I only deal with one direction x. It's also called the vibrating string problem because I have a string, some length in the x direction. It's going to vibrate up and down in both space and time. So it's a partial differential equation, depends on both space and time, but one spatial dimension, that's why it's 1D wave equation. So consider stretch string, pull it tight so that's nice and straight. I have some tension force, T, pulling on both sides. And then I'm going to come along, I'm going to displace this using some other force. That's going to give it some initial displacement or some initial velocity. Then I'm going to let it go, and it's going to vibrate up and down, and I want to quantify those vibrations, again in time and space. So my displacement is going to be called u, and u is going to depend on x and t, and I want to find out what is u for all space and time. Alright, so here's a picture of the scenario. I have my wire originally straight, so the black line is what it looked like before. I then come along and apply this force, it gets pushed down. I have tension on both sides, so it's making it straight. So I have this force, causes this initial displacement along this blue line. And now I'm going to make some assumptions when I solve this equation. First one is that the slope of my deformed wire is small, so probably not drawing to scale, probably a little too big of a displacement here, but so I have a very small slope on both sides here. Elements of the wire can only have transverse displacements, meaning if I look at just this one point here, this one point of my wire is only going to move up and down. It does not move left and right. So whatever point I'm looking at, doesn't matter what point it is, this point right here only moves up and down, does not move left and right. And the last one is that my tangential force in my wire is approximately equal to the tension force. So if I look at the actual force, cut this wire, for example, right here, and what is the force in this direction? What is the force in that direction? They're both equal to T. Again, kind of going back to the first one, small angle displacement, roughly the same tension force. So now what we want to do with the string is look at a small point of it. So I want to look at this point right here, basically this tiny little piece of the string, length dx, so total length of dx. I redrew it down here. So I have a length from center of x, from x minus dx over 2 to x plus dx over 2, so entire length there of the string is dx. On this piece of string, I have three forces. I have the two tension forces. So again, that's supposed to be the same angle. You know, I'm terrible at drawing, but this is supposed to be a straight line. So that tension force is pulling at that angle, calling it alpha. Tension force on this side, pulling again, same direction the string's going, some angle beta. My displacement is now called u. So whatever the displacement of the wire is away from this neutral position, so this is basically u equals 0. That'll be some negative u, be some positive u. So I have some displacements at x minus dx over 2. I have this displacement here, whatever this distance is. At x plus dx over 2, this number here, I have that displacement, so whatever that number is my u values. So I use my displacement. Rho is a linear mass density. You usually think of density as mass divided by volume. Linear mass density, mass divided by length. So again, only dealing with one dimension. All I care about is the length of the string. Length is dx. And then with all these three forces, I want to use Newton's second law. So Newton's second law in the vertical up and down direction, mass times acceleration equals all my forces. So in terms of mass, linear mass density times the length, that gives me a mass. So rho times dx is my mass. Acceleration, second derivative of position in this case being u. So second derivative of position with respect to time, so d squared u dt squared, that's mass times acceleration. Then my forces, I have tension times sine of beta, that's the one on the right going up, minus tension sine alpha, I drew it going down, so I'm going to keep it going down. And then rho g dx, again here's mass, rho times dx is mass, g, gravity, that's the weight of my string. So now to get this equation into a form we can solve, I want to use the approximations that we were making earlier, the small angle approximations. So basically I'm saying my angular slope of my string is not very big. So I had two angles on my previous diagram, alpha and beta, basically saying those two angles are small. So if I have a small angle, sine of an angle, sine of a small angle is approximately the same thing as the tangent of a small angle, which is opposite over adjacent. Opposite over adjacent is the same thing as slope. So the slope of the line, or slope of my wire, is approximately derivative. So another way to do a slope is with a derivative. Here I have du dx. So specifically for alpha, alpha was at x minus dx over 2. So specifically for alpha, sine of alpha is du dx at x minus dx over 2. And similarly for beta, do the same thing. The difference here is that beta is at the location x plus dx over 2. So this guy is the derivative at x plus dx over 2. Now the reason it's going to be important is because I'm going to rearrange Newton's second law in a minute, and I'm going to get a term that looks like this, sine beta minus sine alpha over dx. So I take sine beta, this equation here, ux, derivative of u with respect to x, at x plus dx over 2, and then take away sine alpha, basically same deal at x minus dx over 2. That whole thing is divided by dx. I have some function at some value minus some function at another value divided by the distance between those two values. That's essentially exactly the definition of a derivative. So this is basically a second derivative, one more x derivative, so basically uxx. So as I mentioned, now I'm going to put that into Newton's second law, and we'll see what happens. So Newton's second law we had before. I have rho dx utt. I had that as partial u partial t squared, easier utt. So rho dx utt equals t sine beta minus t sine alpha minus rho dpx. I'm going to divide by rho dx. So divide by rho dx, I'm left with utt on this side. I have t over rho. I can put these two terms together. So sine beta minus sine alpha. There's my term that I looked at previously. And then this just becomes minus g. And so this, as I just showed, is uxx. So I have utt equals t over rho uxx minus g. The last thing I'm going to do is I'm going to assume that there's no forces acting on the string other than that initial displacement, which I'm going to take away. And so it also means that gravity, the weight of the string, is small compared to this tension force. So if it's small compared to the tension force, I can pretty much ignore this g term. Even if I didn't do that, it'd still end up with the same answer. It'd just be a little more complicated derivation to get there, but I'll still end up with this. So one-dimensional wave equation, utt equals t over rho uxx. This is actually more commonly written as utt equals c squared uxx, which is the official one-dimensional wave equation. I basically took this combination tension divided by linear mass density t over rho, take the square root of it. That's what we call c, which is a constant because tension and rho are both constants, so c is also a constant. It's called the wave speed. The reason why it's called the wave speed will be more apparent on Wednesday. So this one-dimensional wave equation, it's a linear, so there's no u's multiplied by each other, so linear equation. Constant coefficients, 1 and a c squared, which is constants, with constant coefficients again. Second order, so again here I have two t derivatives, two x derivatives, highest number there is 2, so second order partial differential equation. We're going to spend the next 2 weeks solving that one-dimensional wave equation. This week we're going to do it one way, next week we're going to do it a different way. Then we'll move on to some other equations the week after that. So as you can probably guess, partial differential equations are much harder to solve than ordinary differential equations. That's why we're doing them now instead of first. Also more variables, more complications to deal with. However, in this case, there's actually a pretty easy way to solve it, and that's what we're going to deal with this week. Next week we'll see kind of a harder way to solve it, but probably more applicable, as we'll see. So for this fairly simple solution, here's my wave equation, utt equals c squared uxx. Solution that I'm proposing is some function of x plus ct, so some function of one variable based on this variable combination, x plus ct, assuming of course this is differentiable twice and you take two derivatives. So any function that's differentiable twice that looks like this, I'm saying solves this equation. So we'll get into more of the details on Wednesday, but before that you have a couple things to do, that I want you to do. First thing, I want you to actually verify what I just said was true. In other words, I want you to verify that this solution, f of x plus ct, is in fact a solution to this equation. And then bonus points if you can actually come up with a second solution to this problem. Remember, we're dealing with a second order equation. Second order equation always is going to have two solutions. I've given you one solution. I want you to see if you can find the second solution. So good luck with that, and I'll see you on Wednesday.